Hi, I'm Don Sheehy, and I'm going to present some research that I did with my PhD student, Kirk Gardner, and it's on computing something we call a kNN sample of a metric space. One way to think about kNN samples is to ask this question of what makes a sample uniform. If I have this set of black points, I can pick out a subset of points that I've highlighted in blue. And this sample is pretty uniform, and in a good geometric sense, this is a great sample. It has points sampled near all of the given points up to some, say, radius epsilon. And no two of the samples are too close to each other, so they're all epsilon apart. That's what we would often call an epsilon net. Now, that's a nice uniform sample in a geometric sense. It's not the uniform samples you may have seen in a statistical context. For example, I might look at this data set and see that on one side of the screen there's a density of points that's like 5 times as dense as on the other side. And so I might expect to get more samples in a good uniform sample if I sampled, say, uniformly with respect to that underlying density. And so this is what a random sample would look like. These two samples I just showed have the same number of points, but their distributions look very different. Now, I get a sample that respects the density when I sample randomly from the set, but I do end up with some oddities. For example, I might get points which are very, very close together, so I don't get this nice spacing condition. You could ask for a sample that achieves the best of both worlds. And what that would look like is something like the following. Now, here, it's a uniform sample, but it seems to be a net with different radii depending on the density. So in the area of high density, you have a smaller radius, but you still have this packing condition that keeps the points from getting too close together. And in the sparser region, the lower density region, you also get a net for a much larger radius. So again, this set of points has the same size, it's the same number of samples as the other two cases, but it seems to achieve the balance between these two. And that's really what kNN sampling is about. So it balances between respecting the density while also maintaining those minimum distances. And the high-level idea is that the distance to 2 points in the sample is approximately the distance to k points in the original set. So I'm going to use this notation throughout. dpk of x is the distance to the kth nearest point to x in the set P. And so with this, I can define the main object of study, which is an alpha beta kNN sample. And so it's going to be a subset of P, which has this property that for every point in the metric space, if I take alpha times the distance to k points, it's less than or equal to the distance to 2 points in my kNN sample, which in turn is less than beta times the distance to k points in P. Okay, so this means that there's an upper and a lower bound on the distance to 2 points in M in terms of the distance to k points in P. Now, previously, we showed how to do kNN sampling in the plane with a kind of Delaunay refinement algorithm. And the way it worked was if you have, say, a Voronoi cell that has too many points in it, if it has more than k, you would add the farthest corner of that Voronoi cell. If you have a Delaunay circumcircle that contains more than k points, then you add the circumcenter, right? And you actually need both of these operations, but if you do, then you can achieve an alpha beta sample in the plane. There is another algorithm. There is a greedy approach to this problem, and it works as follows. As long as some point is too far from the sample compared to its kth nearest neighbor distance, we just add it to the sample. And we just keep doing that until there are no points with this property left. Here it is in pseudocode. It's so simple it almost doesn't merit pseudocode, but I'll just walk through it. This actually explains specifically what it means to be too far. You see, while there's any point P such that dpk of P is less than or equal to 2dm1 of P, then we're going to add P to M. Now, notice this is dm1. That means the distance to 1 point of M. It's dm1, not dm2, because obviously if we add P, that dm1 becomes dm2. now we have two challenges. First, we want to prove that this algorithm actually works. And also, we want to show how to implement it efficiently. First, to show that this algorithm is correct, let's look at the lower bound. If we take any point x in the metric space, and we take the two nearest points in M to x, and without loss of generality, let's just say that this one was added second. Let r be the distance from x to this point. And if we zoom out a bit, we know that that point v1 had another point in the sample within 2r, just by the triangle inequality. And since it was added, it must have had at least k points with distance twice that, or 4r. So the algorithm, which was triggered by having k points too close to v1, added v1, and now by the triangle inequality then, we know that the distance from x to k points was at most 5r, which is at most 5 times the distance to 2 points in M. Now, that's exactly the lower bound now. So dm2 is greater than or equal to 1/5 of dpk, so alpha equals 1/5. For the upper bound, we're going to show that the sample is dense enough that we actually have enough points here, and that is the upper bound on dm2. Let's start with any point x, and suppose that this is a counterexample, that dm2 of x is more than 2 times dpk of x after we've run the algorithm. So inside some ball around x, there are at least k points, and we have to go out twice as far to find a second point in M. Let's define S to be the k nearest neighbors of x. And if we draw the minimum enclosing ball of those points, it has a radius, let's call it r, and that radius, of course, is at most dpk of x because we know that those points all fit in a ball of radius dpk of x. And there must be some point in that set S whose distance to the nearest sample in M is at least r. If all of the points in S were less than r away from a point in M, well, there's only one point in M in the interior of B, so that means the point M would be the center of an even smaller minimum enclosing ball, which would contradict our choice of r. So there's at least one point S that's far, and so dpk of S is less than or equal to 2r, just by the triangle inequality, which now is less than 2 dm1 of S. But if you remember, this was exactly the criterion we used to add S. If the distance to k points was less than twice the distance to the nearest sample, we would have added S, and the algorithm would not have terminated. To efficiently implement this algorithm, one first observation you might make is that it suffices to bound the kNN distance. You don't actually have to compute it. So if I have a point x and I have a nearest sample M, and I look in the ball whose radius is twice the distance to M, then if I find k points in here, then I add x to the sample because I know that the distance to k points then is less than 2 times the distance to the nearest sample. And so I just have to do a range search in this ball of radius 2r around x, and that will suffice. In fact, I don't even have to do the range search, I just have to do a range count, and I can stop once I see k points. I know that I'm going to add the point x. The data structure to implement this efficiently is based on a kind of discrete Voronoi diagram. The points are all associated with their nearest sample, and two samples are going to be neighbors if their distance is less than 3 times their maximum radius. So here's 2 points, P and Q. You can think of abstractly their Voronoi diagram partitions the points, and everyone is associated with their nearest sample. And the farthest of these points to P determines its radius, and the farthest of the points in Q's cell determines its radius. And so we can decide whether or not P and Q are neighbors. Then a greedy permutation is defined by just always adding the farthest point in the largest cell, and then you update the cells and the neighbors. If you do this and you add all the points in this way, you'll get a total running time of n log spread for all the update. But we don't really want to add all the points because sometimes the points are not satisfying the distance condition in the algorithm. Now, we don't want to add all the points, but if we did, we know that we would spend at most n log spread time. You can find this algorithm really laid out in work by Ken Clarkson and its analysis by Harpalet and Mendel. In our case, we want to use this data structure to be able to do a fast range count And by having local neighborhoods all stored together, we can do this quite efficiently, although we have to do a slightly larger range search than in previous work. And so this 3 becomes a 4. Thankfully, all the analysis still goes through. And we end up with a data structure that allows us in n-log spread time to find the next farthest point, but also to be able to find all of the points within the ball of radius 2 times dm1 of x for each x that we consider. So according to the algorithm, some points will not be added. And if we look at them in the greedy ordering, that happens when we looked in the ball of radius 2 times dm1 of the point, and we found fewer than k points. So we take those fewer than k points and we remember them because this point we're ignoring might be one of the k nearest neighbors of that point later when we consider adding it into the sample. If we decide not to add the point, we remember all those fewer than k points, and we put them in a dictionary, and we just check to see if it's in the right ball when it's time to do the search. That adds an extra order k time per point. And so the main result is that if we have a finite metric space with just n points, and I put here that the doubling dimension has to be d. If this is a Euclidean case, you could take the Euclidean dimension to be d, and the spread, or the ratio of largest to smallest distances, is at most delta. Then you end up with this algorithm running in kn log spread time, or as I've written it here, kn log spread plus n log n. And I've highlighted the n log n part here just to point out that that's the heap operations. And we do pay this extra k now when we track unused points. There is an implementation available. You can pip install greedy permutation, and you'll get not only kNN samples, but also one-hop greedy permutations and other greedy permutation implementations. So I encourage you to check that out. Code is all on GitHub. And with that, I will wrap it up. Thank you very much for your attention.